Welcome to the very last homework of Math 451. Congratulations for getting this far. We're going to the computer exercises in section 7.2 and working problem 9. This will exercise the fourth order Runge-Kutta method and hopefully show a significant improvement above the Taylor-based systems, in particular the first order Taylor system, which was also called the Euler method. Okay, where are we going? We're going to take a function, we'll see it on the next page, and we're going to try to solve the first order differential equation that's on the next page between the interval from 0 to 10. We'll take a step size of 0.1, which means that we have 100 intervals that we have to work with. We'll create our solution vector, and we will use a step size of h that corresponds to 0.1 here. And also we'll do all of our indenting and flop calculations. Well, we won't do flop calculations, but we'll at least be sensitive to flops and comments. Okay, here's our differential equation. First order, x of t prime, or the derivative of x with respect to t, is equal to the function t plus 2xt. Here's our starting position. At time 0, x will be 0, and we'll use a step size of 0.1, starting from 0 until we get to 10. We are going to first solve this problem analytically. Now don't panic, that was not part of the homework assignment, so you're not being graded on it. But I want you to see the solution analytically first because it is doable. So let's bring that down here. Here's our differential equation we're trying to solve. And this is doable by the methods of separation, meaning we get one set of variables on one side of the equation and one set of variables on the other. In particular, we want to take the x's and put them on the left and the t's and put them on the right. So let's go ahead and do that. We divide by 1 plus 2x, we multiply by dt, and then we integrate both sides. The integral on the right is easy, that's 1/2 t squared. The integral on the left is also easy. It's the log of 1 plus 2x times a half because of the chain rule. So there's our solution equation, although we would like to solve for x in terms of t. That can be done by taking e to both sides of the equation and doing some other little bit of algebra, and you end up getting x equals 1/2 e to the t squared plus 2k, where k was your constant of integration, minus 1. Now, if you go back up here to our initial conditions, we can find the value of k by plugging in t equal to 0 and plugging x equal to 0 and making this equation work for that initial condition. Well, the only way that's going to happen is if t squared plus 2k is 0, and since t squared is 0, that means the only way that exponent is going to be 0 is if k is 0 itself. That will leave us with e to the 0, which is 1, minus 1, which is 0. So that is basically what this equation down here is trying to do, to prove that k must be 0, and therefore our final solution is shown below. Now just stare at this for a minute, because this solution is kind of an explosive one. As t gets bigger, even if we didn't have a squared term, we know that e to the t grows very rapidly. But as t gets over 1 and then you square it, this argument of the exponential gets bigger yet. So we should expect that this solution will have a very strong upward divergence as t increases, and it's going to make it kind of hard on any differential equation solver. Certainly would make it hard on the Euler method, but we'll just see how our Runge-Kutta method stands up to this challenge. Okay, again, you didn't have to do that, but I'm just doing that for comparison purposes. Well, there again we have our differential equation with initial conditions, and we are now going to do something kind of like we did in 7.1, but instead of trying to just take higher and higher order derivatives, we're going to be a little smarter on where we apply those derivatives. In the case of the Taylor method, maybe starting with the Euler approach, we're looking at its position and its slope at the left end of the interval. And when we add second and third and higher derivatives for the Taylor approach, we are still basing all that curve estimation from that left point. Well, we're going to do something a little bit different here. We'll go ahead and start like that, where we have x prime equals the function itself. But rather than just continuing to ramp up other derivatives, we'll ramp up x and t so that t is going to be halfway up the interval that you happen to be on that has with h, and x will be maybe sort of halfway up the range, which is controlled by f. Well, how can we do that? Well, we'll just simply start with k1 being h times the slope. That's the same thing that we did with the Euler method. But then we'll use k1 to find k2. We'll step up a half an interval from where we were on the left, where t, because t is evaluated on the left of whatever interval we're on, and we will take 1/2 of k, which is maybe halfway up the range, it won't be exactly, and we will reevaluate the function and say that it is another estimate of what's going on with the slope inside this very small interval. Again, multiply it by h, and we have another estimate of change in the function. We could do that a third time. We could take k2, and we could take the same starting value of x and move up 1/2 k2. It's a little different place on the range. And finally, k4 is trying to figure out what's going on at the end of the time period and maybe near the end of the range. So we have 4 different predictors of where the function should go. And our Runge-Kutta method gives us a linear combination to try to give us the best possible change in x to estimate x of t plus h. Okay, so with that, we can now form our MATLAB code.